طيب بسم الله الرحمن الرحيم. We talked last time about EIGRP as a distant vector routing protocol, and we said that fundamentally EIGRP uses partial updates, bounded updates, and triggered updates. And for that, we require the use of the hello protocol, which is used to discover who the neighbors are and also makes sure that these neighbors are alive and well. And if they don't send us hello packets within a dead interval of 3 consecutive time intervals, then we consider them dead. And then we talked also about how to mitigate routing loops in EIGRP. So as we said before, RIP uses split horizon with poison reverse, and also it uses the hold on timer and so on to mitigate routing loops. EIGRP uses the concept or the technique of dual, which allows the routers to maintain in the table some loop-free backup routes. And we talked about the definition of the successor, feasible successor, and the reported distance and the feasible distance. And we said that for the case of loop-free routes to be considered, we have to have the feasibility condition, which states that reported distance has to be less than the feasible distance, in which case the EIGRP process will put this loop-free backup route in the topology table. So EIGRP uses two types of tables: of course, the routing table and the topology table. So this will allow EIGRP to have fast conversions and mitigate the routing loops. So today, inshallah, we're going to start by a link state routing protocol. So of course, we ask ourselves, so how link state routing protocols mitigate routing loops? In fact, there's no routing loops in link state routing protocols because they maintain global view. So the global view of the entire autonomous system is well known and maintained by every individual router in the autonomous system. So every individual router independently will get the full map of the entire autonomous system locally. And we'll see how this happens. Based on this, link state routing protocols, they use what we call shortest path first. So if we have the full map, we can get the shortest path between any 2 points using any metric we want, because we have the entire map, so we can do whatever we want. In order to construct the shortest path, we use a technique which is called Dijkstra, an algorithm called Dijkstra's algorithm to calculate what we call shortest path tree from one point to all other points in the autonomous system. So we'll see how that happens in a minute. So this is the global view, and this global view is very well known by every single router in the autonomous system. So every single router has this full map. So router 1 can independently calculate the shortest path from router 1 to router 2, from router 1 to router 3, from router 1 to router 4, from router 1 to router 5. Constructing what we call the shortest path tree. So for example, if we want to know the shortest path from router 1 to router 5, then we can calculate based on the cost, of course. So we know the cost of every single link. Okay, so router 1 will say, to reach to router 2, I will possibly have to go directly to router 2. To go to router 3, I will have to go directly to router 3. Right? But if I want to go to router 4, we will see that we have to go through router 3 first and then router 4. This will have a less accumulated cost because 5 plus 10 is less than 20, right? Similarly, if I want to go to router 5, then I have to go through router 3 first and then router 4 and then router 5. So in fact, this black, I better do it red, actually, it's better. This red lines constitute what we call the shortest path tree from router 1 to all the other routers in the autonomous system. So this is what we call the shortest path tree. So the total cost from any destination here to router 5, it's actually 2 plus 5 plus 10 plus 10, which is 27. So we can calculate everything because we have the full map locally at every single router in the autonomous system. So we know exactly the total cost from one point to any other point in the system. Be done easily for link state routing protocol because we have a global view. So the question is about how to calculate this global view or how to collect this global view. This is what we will discuss now. So the shortest path, as we all know, doesn't necessarily have to be the least number of hubs, because, you know, for example, if we want to reach to, for example, R5, so if we go with the number of hubs, it's either this way or this way. Each of these paths will lead to 2 hubs, okay? So in that case, rep will do, the rep will simply say, oh, okay, so R1 to R5, I can go through R2 first, or I can go through R4 first, and both of them, they will have the same cost of 2 hubs. So in that case, rep will do load balancing between the two because the two have the same cost. However, if we talk about link state routing protocols, link state routing protocols do not use the hub count as the metric. They use the bandwidth, as we will see in a minute. So in that case, the cost, the least cost is neither of these two. It's neither to go to R2 nor to go to R4. It's actually to go to R3 first, doing this and this and this. This is actually the shortest path because it has the least cost, which is based on the bandwidth in that case. Okay, so this table is constructed based on the fact that you have a source node here, and this is to construct the cost to reach from this node all the way to any other node in the system. So to go to R2, for example, then we need 2 and then 2, so the cost is 22. Okay, to go to R3, so the cost will be 7. To go to R4, the cost will be 17, and to go to R5, the cost is 27. Okay, so that's, of course, we can do this visually because we have the map in front of us. But how do the routers in link state routing protocols, how do these routers systematically get this information and get to this routing table? So this routing table is our ultimate goal, is to have this routing table, you know, calculated and estimated and be in a stable condition for all the routers to work correctly. So in order to do that, we'll see that we have five different steps. Okay, so 5 steps to reach to the state that we have a fully operational routing table. The first thing that's done by each router individually is that each router will collect the directly connected links. Okay. From the name, of course, we talk here about link state. Link state means that each link will have its own details in terms of what is the default bandwidth, of course, if this link is alive and well, and so on and so forth. What type of link it is, and so this is for example an example of a link state. Okay, so each of these links are directly connected to R1, and as we have discussed before, R1 will get by default the details about all these links because they are directly connected. Okay, so all the link states of the directly connected links are known by R1. So R1 will have to first get the link states of the directly connected link. Number 1. Step number 2, because as we have discussed, link state routing protocols, they use triggered updates, or they use actually an update based on updated link. So if the link goes down, if the link goes up, that's only when we send the routing updates. So routing updates for link state are not periodic. So similar to EIGRP, and that's why we said that EIGRP is kind of hybrid. It's kind of a hybrid protocol. So similar to EIGRP, because EIGRP also uses triggered updates, not periodic updates. Any protocol that uses, triggered updates, it requires first to discover who my neighbors are. Okay, so in order to send a triggered update, I need to discover who my neighbors are. Why? Because just the fact that R1 and R2 are connected using physical link, it doesn't mean that they are neighbors. Okay, they are not necessarily neighbors. Similar to EIGRP, we said that EIGRP defines the neighbor using what? Using the autonomous system number. Here is different. We'll talk about it. But so just the fact that two routers are physically connected to each other, it doesn't mean that they are necessarily neighbors, right? So first, I need to discover who my neighbors are. So I need the, similar to EIGRP, I need to use hello protocol. So again, hello packets are periodic and broadcast packets, similar to EIGRP. So the hello protocol is used for two things. It's used to discover who my neighbors are. Okay, so first I need to know all the routers that I'm connected to physically, are they really my neighbors? Okay, so this is one. Two, are all of them alive and well? Which means that if I don't receive hello packets from any neighboring router for 3 consecutive times, here actually it's four consecutive times, then I consider that this router is dead, which means that the link between me and this router is down, and then I need to do something about it. So number 2 is to discover who my neighbors are and to make sure that these neighbors are alive and well. So this is step number 2. So these hello packets are sent to all the neighbors. So every router will have to exchange these hello packets with the neighbors. And as we will see, the hello packets are sent in a form of multicast, which of course includes broadcast. And then if two routers are neighbors, then they will keep exchanging these hello packets to act as one, discover that we are neighbors, two, to make sure that we keep each other alive and fresh with the fact that we are working and operational. That's the purpose of the hello packets. Type. So once I do this, step number 3 is to collect all the link states of the directly connected links and form what we call link state packet. Link state packet will contain the link states, these link states of all the directly connected ones. So for example, R1 will collect the link state here, link state here, link state here, and the link state here. So router 1 will form a link state packet that contains 4 link states, and then it starts to exchange these with all the other routers in the network. One thing to notice here is that these link state packets will be sent, okay, in a form of multicast, but they are actually forwarded by other routers, which means that they have to flood the entire network. Okay, so of course I have to send the link state packet to my neighbors only, which means in a form of multicast. But then all the neighbors, they have to forward this link state packets to all other neighbors and so on, until everyone in the autonomous system gets a copy of this link state packet, and then they have to form their own link state table, as we will see. So link state packets are flooded. Very important. Flooding means that not only do they get sent using multicast, but all the ones that will receive. So R1, for example, will send link state packet to R2. So R2 will receive this link state packet, will have to send it to all its neighbors. Okay, and so on. So here we'll go to here and here. So it has to reach the entire system. It has to reach to the entire network, right? Unlike EIGRP, because EIGRP, remember, uses vector of distances. Vector of distances are sent as one hub multicast. One hub multicast. They don't get flooded. I hope the difference is clear. Huh? They don't get flooded into the network. They send as one hub multicast. That's why distant vector routing protocols, they maintain a partial view. They don't maintain a global view. ماشي كده؟ So this is the difference. After receiving link state packets, the neighbors will have to forward this further to all the others. ماشي كده؟ طيب. So step number four بقى, the routers, they will construct what we call link state database. Link state database contains all the link states of all the links in the autonomous system, supposedly, but we will see يعني, that it's not exactly like this. So routers, they use this database to construct the topology map of the entire network. Type. Just to review quickly, RIP uses only routing table, nothing else, right? EIGRP uses two tables, right? Using routing table and topology table, right? Link state routing protocols, they use three tables. Routing table, topology table, because we use hello protocol, and the third one is link state table. Link state table maintains the global view of the entire network. ماشي كده؟ So once we have this link state database constructed with all the link states, this link state database, by the way, is identical at every single router. It has to be identical. So the link state table has to be constructed the exact same way locally at every single router. So this is how the link state table looks like. At R1 will have to know all the link states to all the routers, and to this one, every single link state, it will have to be known by each individual router, which means that this link state database will have to be constructed similarly at every single router. So step number five is that to run the Dijkstra's algorithm to construct this routing table from the link state table, right? So this is the last step. So once we construct this routing table, our job is done. ماشي كده؟ So so the way that Dijkstra algorithm runs or works is to construct what we call shortest path first tree. Okay, which in that case, R1 will have to, the Dijkstra algorithm will have to run at R1, analyzes all the link states in the link state table, okay, and then it will know that, okay, so to go from any source node on this LAN, okay, if I want to go to any destination on R2, then I can go directly into R2, and if I want to go to R3, then I can go directly. If I want to go to R4, then I have to go through R3 and then R4 and then R5. So the blue lines constitute the shortest path tree, which is the tree that forms the shortest path from one point to every other point in the network. Okay, so this is what we call the shortest path tree, which in fact corresponds to the routing table. So if I want to go from one source here to any other destination, these are the least cost that belong to the shortest path tree. And as we can see, except for R2 that we have to go directly, every other destination we will have to go through R3. Okay, so this is what we call the shortest path tree from one of the nodes in the network. Okay, So these are the 5 steps through which the link state routing protocols, they will construct the routing table. ماشي? So this is the way, or the systematic steps that we take, 5 different steps to form the routing table for the link state routing protocol. So what are the characteristics of the link state routing protocol? Well, in terms of memory requirements, we discussed these before when we talked about distant vector routing protocol, if you remember. So we discussed 3 different criteria, right? So we said for memory requirements, link state routing protocols, they tend to have more storage requirements. Why? Because we have to maintain 3 different tables, unlike distant vector routing protocols, which needs only 2 or 1 table for the case of RIP. Here we have 1 extra table which has to account for the link state database to maintain this global view, right? In terms of processing requirements, also it's high because the Dijkstra algorithm has to run through the global view, right? Not like the distant vector routing protocols, where we just run, again, it's just partial view or a small view. So in that case, it's in terms of computation, the computation requirements is low for the case of a distant vector. Here it's much higher because of the fact that we have to run against the link state database and the global view, and in that case the processing requirements is higher. In terms of bandwidth requirements, in terms of sending the link state updates, it's kind of interesting because it varies because link state updates are sent in a form of triggered update. However, at the beginning of the operation, we know that each router has to collect all the link states and flood it into the network. So that's why, in terms of bandwidth requirements, initially, so if I were to simulate it كده, what is the bandwidth requirement for sending route updates? Bandwidth, or for some in some cases we call it overhead, okay, as a function of time. So when the network first starts, it would be like very, very high, right? And then it will be very low, and then by it may vary like this based on any updates that might happen in the system. But this accounts for the initial phase where each router has to collect the entire global view of the entire system. That's why we need at the beginning very high bandwidth to exchange these link state updates. Okay? Any question يا شباب so far? Okay. طيب. So this is an introduction about link state routing protocols. So to talk about a specific link state routing protocol, we talk about open shortest path first protocol. Open shortest path first. So OSPF is a standard. It's developed by IETF. It has an RFC, okay? And OSPF uses, again, similar concept. We see some similarities between OSPF and EIGRP, although there are some significant differences. So we need to know what these differences are. So first, when we talk about the protocol data unit for OSPF, we see that we have the data link layer header, and the data link layer header contains a multicast physical address. Because as we said, just the fact that we are physically connected to each other, it doesn't mean that we are neighbors, okay? So in general, I need to send multicast. And if you remember, you see this interesting number. If you remember from network 1, 01005E, if you remember it from network 1, that's a multicast physical address, right? So in general, OSPF uses a multicast physical address. Also here, in the IP packet header, we also use multicast IP address, right? And again, but similar to EIGRP, OSPF uses its own transport layer protocol. Okay. However, this transport layer protocol is unreliable by default. Okay. So unlike EIGRP, which uses reliable transport protocol, remember, EIGRP uses RTP, reliable transport protocol. OSPF uses unreliable transport layer protocol. So here, we will not see here, if you take a look for the packet header, OSPF packet header, we will not see any kind of acknowledgement or sequence number or something like this. But interestingly speaking, we will see that here we have a link state acknowledgement, which is one of the types of messages that we send at the application level. Okay, so that's interesting. So the explanation for this is that the reliability or the confirmation that the link state update has been received is from the application level, not from the transport level, right? So transport layer is by default unreliable, but the reliability comes from the application layer. So this is just something to take a look at or to remember. Yeah, ماشي. But as we will see, the transport layer itself does not have any sequence or acknowledgement or any kind of reliability. However, the OSPF packet header contains two very important fields, which we will talk about: the router ID and the area ID. Router ID and the area ID. And of course, the packet type, which corresponds to the opcode for the case of EIGRP. And this opcode also has 5 types similar to EIGRP. We have the hello packet, okay? And then we have 4 other types that we need to talk about, which is slightly different compared to EIGRP, okay? Any questions so far? So these are the 5 types. Of course, the hello packet we all know about. It's used to discover neighbors and build adjacencies. And then we have something called database description. And then we have link state request, link state update, link state acknowledgement. Okay, so we will have to go through these and see what these 5 types are used for. Okay, database description is used for database synchronization. So we'll know exactly what this means. And then request, and then update, and then acknowledgement. Type. So this is the how the protocol format looks like. So if we take a look here, again in the transport level, so this OSPF packet header in the transport level, we have the type, right? The type of the message, and here one means that it's a hello message, and this is how the hello message looks like. Okay, and we'll see what this means. Then we have something called router ID and area ID, right? So so the transport layer header contains, as you can see, it does not contain any kind of sequence number, acknowledgement, flags, things like that, because the transport layer header or the transport layer protocol that OSPF uses is actually unreliable, right? It's a specific protocol for OSPF, similar to EIGRP, but here it's unreliable by default. So what is this router ID and area ID? What is this designated router and backup designated router type? So very importantly بقى, we need to discuss بقى conceptually. احنا قلنا the routers they exist in one autonomous system. Okay, so rep and EIGRP deal with the autonomous system as one unit, okay, or one logical domain under the control of one authority. OSPF uses a slightly different concept. It actually subdivides the autonomous system, okay, into what we call areas. Okay, so you can think of areas as clusters. So unlike EIGRP or OSPF, or REP, OSPF actually clusters the routers inside the autonomous system into clusters. Okay, so here you have like few routers like this that form clusters. Okay, for each cluster, we have what we call the cluster head. The cluster head, we call it a designated router. Okay, so each cluster will have a cluster head, which we call it a designated router. OSPF, for fault tolerance, in case the designated router goes down or it fails for some reason, it uses what we call a backup designated router. Okay, so the backup designated router acts as a backup cluster head in case this designated router goes down. Okay, so this backup designated router and designated router are cluster head, and each head we call it an area. So each cluster we call it area. So the OSPF deals with clusters as area, and that's why we have here the area ID and the router ID. So this is the source router in the area ID, and it sends this to the designated router and the backup designated router. Okay, so even hello packets, they have to be sent from any router in the cluster. It has to be sent to the designated router and the backup designated router. Okay, and then from the designated router will then send this to send the link state update to all the other routers. So that's why in clusters we have cluster head. Cluster head means what? That all types of communication, they have to go through the cluster head. Okay, so that's the concept of area or a cluster in the case of OSPF. All right, so every kind of every type of message, it gets sent first to the designated router or to the cluster head. But of course, because we have a backup designated router, then we have to send to two, the designated router and the backup designated router, for fault tolerance. Of course, the backup designated router will take over the responsibility of being the designated router in case that designated router goes down. So that's why we have the hello packet format. It looks like this to get exchange between routers in the same area. So in the same area, all the messages have to be sent to the designated router and the backup designated router. ماشي كده؟ So that's for the case of the hello packets. Okay. طيب. So the hello packets, they contain, of course, as we said, the hello packets, even the hello packets, they use a multicast. Why? Because I may actually be connected to a router in another area physically, but I don't send to this router. I actually have to send to the designated router and the backup designated router, and then from there I have to send to others. Type again, the hello packets are sent in a form of periodic, and it's sent every 30 seconds. Okay, in the case of so here it's sent every 10 seconds. But in the case of non-broadcast multi-access network topology, remember this topology is where you have a hub and it connects with many routers like this. And as we said that for these types of topologies, we have to reduce the frequency of the hello packets, right? So in case of OSPF, the standard defines 10 seconds as the default value for the period of sending the hello packets. For EIGRP, if you remember, it was 5, yani. And for the case of non-broadcast multi-access topology, it's 30 seconds. In the case of EIGRP, it was 60 seconds. Not that it makes a big difference, yani, but yani, the standards, they have to define some default values, which the network analyst is allowed to change at any point of time. The dead interval here means that if you do not send hello packets, if a router does not receive hello packets from a specific neighbor for 4 consecutive times, which in that case 40 seconds, if I do not receive a hello packet from the neighboring router for 40 seconds, then I declare this router as dead. And then the link between me and this router, the link state is changed. Then I have to send trigger updates to other routers and so on. ماشي كده؟ Any questions so far? So this is the concept of cluster head, or the designated router, and the backup designated router. Okay, so I have designated router and the backup. I keep the backup designated router engaged in all communication. Why? Because at any point of time, if this designated router becomes down, I can switch seamlessly without any transitional period. That's why the backup designated router has to be engaged in the communication all the time, right? And that's why I have to use multicast and send to both at the same time. Forget about this part. Forget about this part. This part is removed. So as we said, once I know who my neighbors are, I can then send the link state updates. And the way we do this, remember, the way we do this, the sequence is as follows. So first, router 1 and router 2, okay, using the hello protocol and everything, they have discovered that they are neighbors, right? Router 1 has some link states. Let's say link state 1, link state 2, طبعا with the details and everything, link state 3, and so on. Router 2 has link state 1, link state 3, link state 4, and so on. And everything is detailed, right? So first, each two neighboring routers, they will have to send what we call database description. The database description message, okay, which is of type 2, this database description message, it will contain all the link states that router 1 has, which in that case is link state 1, link state 2, and link state 3. Okay. Router 2 will receive this database description. It will realize that, okay, I have already link state 1, I have already I have link state 3, but link state 2 is missing. Okay. Similarly, router 2 will send this database description to router 1, and then router 1 will say, yes, I have link state 1, I have link state 2, okay, I do not have link state 4. Okay, so router 1 is missing link state 4, router 2 is missing link state 2. So based on that, they will start to exchange what we call a link state request. So router 2 will then send link state request to router 1 with link state 2. Remember, when I send the database description, I only send the ID of the link. I don't send the details. Huh? So it acts as database synchronization. So I send the IDs, okay, and then router 2 will say, I don't have the details of link state 2. So it sends a link state request to R1 with a link state ID of 2. Similarly, R1 will send link state request with link state of 4. Okay. Then R1 will reply back to, or will send the link state update to R2 with link state 2 with all its details. Similarly, R2 will send link state update to R1 with link state 4 and all its details. And then the two routers, they will become asynchronized in terms of link state database. Okay, so that's the sequence. And of course, link state update requires acknowledgement. So all of them, they will have to send برضو a link state acknowledgement. So the sequence is, once we discover that we are neighbors, we have to first synchronize our databases using database description, right? If we have any missing link state, then we send link state request. Okay. Then the other router will send link state update, and then we send link state acknowledgement. So that's the sequence. So these are the 5 messages that we have here. ماشي كده يا شباب؟ Any questions? Yes, bravo عليك. Yes, I like the fact that you are focusing and you have. So link state advertisement or link state update, both of them are exactly the same. Okay, so these are terminology for the same thing. Link state update or link state advertisement, both of them are the same thing. Okay, so link state update can be a result of link state request coming from a router, or it can be sent triggered based on the fact that one link is down. One of the directly connected links is down. ماشي? So again, so let's remove this. So a router 1 now has all the links for the directly connected links, and it also receives a link state request from other routers. Okay, so it may in fact send link state update as a result of the link state request coming from a neighboring router, or one of these links goes down, in which case I also have to send triggered update. Okay, so in that case, I send link state update or link state advertisement. There is no distinction between the two. Okay, with the fact that the link state of this link has been updated. ماشي؟ The questions يا شباب. So the OSPF router builds this link state table, right? Based on the 2 steps we have talked about before. We have to collect the directly connected links. We have to do the hello protocol, okay? And we have to send the link state update, okay? We form the link state database. Once we form the link state database, then we run the Dijkstra algorithm. We run the Dijkstra algorithm to form the shortest path tree that contains the shortest path from one single point to all other points in the network. So for example, from here to R2 and to R3 and to all other destinations in the network. Okay. So we in step number 5, we form the routing table, which will be the ultimate goal of any link state routing protocol. ماشي؟ طيب, we talked about the fact that EIGRP uses the concept of autonomous system number. Remember that again, if how do we consider 2 routers as neighbors? Router 1 and router 2. Okay, if they are physically connected, it doesn't mean that they are neighbors, and in order for them to be neighbors, then we have the autonomous system number, which it has to match between the 2 in order to consider that these 2 routers are neighbors, right? In OSPF, the concept is different. The concept is different. That's why here, when we run the OSPF, we say router OSPF and then process ID. We don't call it autonomous system number. Why? Because the process ID for the case of OSPF is not used to identify neighbors, or it's not a condition to consider each other a neighbor. ماشي? So even if this is 1 and this is 2, okay, we consider each other, we can still consider each other a neighbor. Type. Then what is the purpose of the process ID? From the name, it's a process ID, which means that I can in fact run on the same router 2 OSPF processes or 3. Okay, هتقول لي why do you do this? For parallel computation only. So the process ID has a local significance. Unlike EIGRP, the 2 autonomous system numbers, they have to match. In order for us to consider each other neighbors, the 2 autonomous system numbers, they have to match. And that's why we call it a autonomous system number, بوضوح, because it has to match between 2 routers in order for these routers to consider each other neighbors. Okay, for OSPF, it's called process ID. Why? Because in fact, it's only used for parallel computation. Okay, it's only used for parallel computation. So, you want to increase the computational power of OSPF, so you can run multiple instances. But these 2 routers, they are considered neighbors if they exist in the same area. That's what this means. If they report or if they are connected to the same designated router. Okay, so then they exist in the same area, in which case they are neighbors. ماشي? So process ID, again, for the case of OSPF, has local significance, and it's not a condition for routers to identify each other as neighbors. طيب. The metric for the case of EIGRP, if you remember, it's based on 2 parameters. It's based on the bandwidth and the delay, at least two طبعا, or optionally 4. Delay, bandwidth, reliability, and load. Reliability and load are optional, right? For the case of OSPF, it's simple. It's only based on the bandwidth. And the way that the metric is calculated for the case of OSPF is that you have a reference bandwidth, okay, which is defined for the entire system. This reference bandwidth could be, or by default, it's 10 to the power 8, which means that the reference bandwidth is in fact 100 megabits per second. 100 megabits per second. This is the reference bandwidth, okay? And the bandwidth, the theoretical bandwidth of the link, okay, will be the denominator. So the cost of any link will be the ratio between the reference bandwidth and the bandwidth of the link. So if you have a fast Ethernet has a theoretical bandwidth of 100 megabits per second. So the cost of the fast Ethernet will be 1. ماشي كده؟ The cost of Ethernet is 10 megabits per second, in which case the cost is 10. طيب, what if I have 10 gigabit per second اللي هي ultimately fast Ethernet? In that case, you need to change this reference bandwidth. Okay, so it will become 10 to the power 10 in that case. Because the cost of OSPF has to be 1 or more. يعني. OSPF maintains the cost to be 1 or more. So in any case, it doesn't matter. But we have to know that the cost of any link is actually the reference bandwidth, which is fixed, divided by the theoretical bandwidth of the link. Okay, and the default is, look here, 64 here means that the theoretical bandwidth of the link, is 1.544 megabits per second. So in that case, 10 to the power 8 divided by this is around 64. And this is the cost. This is for T1 connection. T1 is typically the the link, if we were to use serial point-to-point between two routers, usually we use T1 connection, in which case the bandwidth is 1.544 megabits per second, and in that case the cost is 64, right? So I think that's all about the OSPF. as a recap, 100 megabit per second. So an example for a network like this, what is the cost of this fast Ethernet? This is fast Ethernet, so the cost is 1 because the bandwidth is actually 100 megabit per second, so the cost is 1. This link, the cost is 64. So if you here, we see that the cost for this link, because it's a serial point-to-point, is actually 64. Okay. So between R1 and R2, the theoretical bandwidth is actually, the theoretical bandwidth is 1.544 megabits per second. ماشي كده؟ So in that case, the cost is 64. So if I want to calculate the cost from any source node here to R1, what would be the cost? What is the cost in that case? 65, bravo عليك, which is 1 plus 1 plus 64. Very simple. 1 plus. There are two interesting observations here. I'm hoping that you can detect them. One, we said that the end-to-end bandwidth, okay, as we said before, bandwidth is a bottleneck parameter, صح? Which means that the end-to-end bandwidth, okay, the total cost when it comes to bandwidth is actually the minimum bandwidth, right? The minimum bandwidth. So it should be this one or this one, whichever has minimum bandwidth. So in that case, of course, this one has minimum bandwidth for higher cost, so the cost is 64. لا. The OSPF uses the bandwidth, however, it accumulates the cost of the link. Why? Because, in fact, the cost is based on 10 to the power 8 divided by the bandwidth. What is the inverse of the bandwidth? It's actually the delay. The inverse of the bandwidth is actually a delay. So it makes sense to accumulate the delay, right? But the bandwidth itself is a bottleneck parameter. That's why for EIGRP, the bandwidth of the link, the bandwidth, sorry, of end-to-end path is based on the minimum bandwidth across the entire path. Okay, why? Because the matrix still contains the delay. Because the matrix for EIGRP contains both the bandwidth and the delay, right? The bandwidth and the delay. Here, the delay is actually not there, but in fact, the inverse of the bandwidth gives some idea about the delay. And in that case, we can accumulate the cost of all the links, because essentially we are accumulating delays, not so the unit of this bandwidth becomes a second. Okay, the unit of this cost, because it's inverse of the bandwidth, so it's delay, and that's why we can accumulate the delay, right? So that's observation number 1. Observation number 2. If you take a look here, I actually I tricked you and I said that the cost here is 64, which means that the theoretical bandwidth on this link is 1.544 megabits per second, right? But here it shows 64 kilobits per second. That's not a typo. This is not a typo. The 64 kilobits per second is in fact not the theoretical bandwidth. It's called the actual bandwidth. Okay, this is the actual bandwidth, not the theoretical bandwidth. This is just a يعني a detailed point. يعني it's not very important, but just we talk about it for completeness. So this is actually the actual bandwidth, not the detailed bandwidth, not the the theoretical bandwidth. By default, OSPF will take the theoretical bandwidth. يعني بمعنى once R1 starts, it detects that this link is a T1 connection. So by default, it uses cost of 64 على طول. Okay. So what if the network designer knows that the actual bandwidth of this link is less than the theoretical bandwidth? So in that case, the network designer has to go manually to this interface and change its bandwidth from 1.544 to 64 kilobits per second. It will have to change the default bandwidth of this link in order for OSPF to calculate this cost differently. So in which case, طبعا, the cost will be a lot more than 64. Okay, it will be higher than 64 because this bandwidth is less. It's 64 kilobits per second. Recap. يعني a minor point يعني بس ايه. So there is a difference between the actual speed, okay, and the default bandwidth. So the actual bandwidth may be less than the theoretical or the default bandwidth. So in that case, if you show the interface here, the interface will show the default bandwidth. If the network designer knows that the actual bandwidth is less for some limitations on this link, okay, then it has to go directly to this link and say bandwidth, and then it says 64 kilobits per second. In that case, by OSPF will pick up this new bandwidth, and then it will say, okay, so the cost on this link will be 10 to the power 8 divided by 64,000, which will be very high in that case, right? So that's the difference يعني, between the actual bandwidth and the default bandwidth. Okay, so OSPF, or for distant vector, for link state routing protocols, we talked about a global view, and this global view is achieved through many steps. The first one is that first, each router will have to connect the link states of all the directly connected links, form the link state packet, and then number two, it will have to discover its neighbors by sending the hello packets. Hello packets are sent periodically, every 10 seconds in the case of OSPF. And by exchanging these hello packets with the designated router and the backup designated router in the area, I know exactly which routers are neighbors, which means that they exist in the same area, in which case I need to exchange some routing information with the neighbors. Routing information starts with first by sending a database description to synchronize the tables, the link state tables between two routers. So each two routers, they will have to send database descriptions to the backup router, or the designated router and the backup designated routers, which will be exchanged with other neighbors in the area, based on which the router would know which link states are missing from its table. Then it sends a link state request. Okay, it sends a link state request with the link state that's missing. Then it receives a link state update. It updates its table, and then it collects all the link states in the link state database. Then step number 4, it actually, or the last step, is that it runs the Dijkstra algorithm against the link state table to form the shortest path tree, which populates the routing table directly. For the case of OSPF, as we said, OSPF maintains 3 different tables: the topology table, and of course the link state table and the routing table. It maintains all these 3 tables all together. ماشي كده يا شباب؟ Any questions? Okay.